So guys, let's continue our discussion over the same, which was finding the inverse of the sine function. We had recently seen that if I take this as my domain, this as the codomain, then situation is not becoming anything good, because this domain is not allowing my sine function to become 1, 1. This codomain is not allowing my sine function to become onto. It is too large. It is so large that it is containing so many elements which are getting mapped to the same member, because of which my sine function is failing to become 1, 1. And this codomain is so large that it is containing so many members, and many members are there which do not have any preimage. So to avoid repetitive of images, basically to avoid members which are having the same image, and to avoid members which are not having any preimage, I will have to shorten up the domain and shorten up the codomain, right? From R to R it is neither 1, 1 nor onto. Therefore, there is absolutely no question of finding the sine inverse from R to R, right? Let's move to the next step. Now, I will be first of all teaching you how to make or shorten up your codomain to just that section which consists of members, such that each member has at least one preimage. What we are going to do is, we understood that from -1 to 1, each member has at least one preimage, and beneath -1 and beyond 1, no member has even one preimage. So I am going to take my codomain as -1, 1 closed interval. That is it. I am chucking out all the members before -1, chucking out all the members beyond 1, because they are hindering my sine function from becoming onto. So I am shortening my codomain and keeping it, restricting it to just the range. Yes, that is the tactics. Tactics is restrict your codomain to just the range. Range consists of all those members which are the images of some members from the domain, right? From the domain, if you take the domain members, all their images are nothing but -1, 1 closed interval. That is the range. Range of the sine function is -1, 1 closed interval. So if you restrict your codomain to just the range, you are actually restricting your codomain to that section which consists of members which have at least one preimage. So therefore, I restrict my sine function's codomain to just the range, restrict codomain to the range. When you restrict codomain to the range, your function becomes onto. Because right now, if you see each member, now this is the new codomain, this is the new codomain, Now if you see, every member of this codomain has at least one preimage in the collection of all reals, which is my domain, right? So because each member in the codomain now, new codomain, manipulated codomain, each member here has at least one preimage. In fact, it has so many preimages in the collection of all reals, you know that. So therefore, from R to -1, 1, it is an onto function. Sin x from R to -1, 1 is onto function. Clear? So ontoness is treated. Cool. One step ahead we have moved. We want to make sin 1, 1 as well as onto. 1, 1s is the problem, or basically it's the feature devoted by the domain members, and ontoness is the feature which is given by the codomain members. We have treated the codomain by restricting it to the range and hence endowing the sine function with the ontoness feature. Now our task is to treat the domain to endow my function to get the 1, 1 feature. Please understand, try to imagine if I rub this section, this complete section, because now my new codomain does not involve this section, right? It does not involve this section. If I keep only this section of -1, 1 closed interval, right? And the domain is collection of all reals only, even then you can see that my function is not 1, 1, isn't it? At 0 I am getting 0, at pi I am getting 0, at 2 pi I am getting 0, at minus pi I am getting 0, at minus 2 pi I am getting 0. So when I have changed my codomain from collection of all reals to minus 1, 1 closed interval, 1, 1ness is not treated, only ontoness is treated. Now there is no member in the codomain which has no preimage. Every member in this new codomain now has at least one preimage. So now you can see that by restricting my codomain to the range, only ontoness is being treated, 1, 1ness is not treated. To treat the 1, 1ness, I will have to somehow restrict my domain to that section corresponding to which the graph of sine has no turns. What is it which is causing this horizontal line intersect the graph at more than one point? Because there are curves, there are turns, you can see there are turns. That is why whenever you draw a horizontal line, it is going to intersect the graph of sine at more than one point. If there is absolutely like an increasing type of a behavior of the function or decreasing type of a behavior of the function, in that case when you draw horizontal lines across the graph, they are going to intersect the graph at exactly one point. But because there is turn in the graph, any type of turn in the graph is going to cause the horizontal line across the graph intersect the graph at more than one point. So now my task is to restrict this entire real line to such a section corresponding to which the graph of the sine function has no turns, because then only my 1, 1ness will be established, because then only when I will be drawing any horizontal line across the graph, it will be intersecting the graph at only one point. So look at now that section of the real line corresponding to which I am getting no turns, as well as corresponding to which the ontoness of the function should not be disturbed. Fine? Okay. If I restrict my real line to this section 0 to pi, suppose I restrict my real line to this section 0 to pi, corresponding to 0 to pi, this is the behavior of the function, right? This is the behavior of the function. There is a turn involved, I cannot take this section. Fine. If I take the section minus pi to 0, again this is the graph. Turn is involved, I cannot take this section. When I will be drawing a horizontal line, it will be intersecting this portion at more than one point. Moreover, another reason to not take this section is when I am taking 0 to pi only as the restricted domain, only 0 to 1 image members are being covered. There is no member in 0 to pi which has image in 0 to minus 1 or minus 1 to 0 interval, right? There is no member in 0 to pi which has image in minus 1 to 0 interval. So from 0 to pi, 0 comma pi to minus 1, 1, the function will fail to be onto, right? From 0 comma pi to minus 1, 1 function will fail to be onto, because in every member in 0 to pi has image in only 0 to 1 section of minus 1, 1 closed interval. There is no member in 0 comma pi which has image in minus 1 to 0 closed interval. So minus 1 to 0 section is not going to have any pre-image. So therefore my ontoness will be disturbed if I restrict my real line to 0 comma pi. Similarly, ontoness will be disturbed if I restrict my real line to minus 1 to 0, because no member in minus 1 to 0 has image as 0 to 1 interval, has image in 0 to 1 interval. So 0 to 1 interval of the codomain will have absolutely no pre-image, so again ontoness will be disturbed. I want such a section corresponding to which there is no turn as well as ontoness is not disturbed, and that is this section, minus pi by 2 to pi by 2. If you restrict your domain, which is the collection of all reals, in minus pi by 2 interval, in that case the graph which is going to follow corresponding to this section of the domain is this graph. You can now see there is absolutely no turn in the graph of sine corresponding to minus pi by 2 closed interval. Moreover, if you see, all the members from minus 1, 1 are being accepted as images. You can see corresponding to this I am getting minus 1, then here, then here, then here, corresponding to 0 I am getting 0, then here, then here, then here, and corresponding to pi by 2 I am getting 1. So all the members of minus 1, 1, minus 1 comma 1 interval are being obtained as images corresponding to members in minus pi by 2 closed interval. Are you understanding? And there is absolutely no turn also. Now if you just consider this section minus pi by 2 as the domain and consider this as the graph, that is the graph. What you do, you draw any horizontal line across this graph, you are going to find that any horizontal line intersects this graph at exactly one point, corresponding to minus pi by 2 closed interval, right? Therefore, this is how we restrict our domain of the sine function so that ontoness is not disturbed and the function comes out to be 1, 1. What do we do? After this step, we treat the 1, 1ness. We say sine x from minus pi by 2 closed interval to minus 1, 1 closed interval. What is this? I have restricted my domain, which is collection of all reals, to the section corresponding to which there does not exist any turn in the graph of sine and ontoness is not disturbed. These are the grounds on the basis of which I have restricted my domain to minus pi by 2 closed interval. Sine function from here to here is definitely 1, 1, and because I have restricted already my codomain to the range, it is onto as well. So I have attained success. I have manipulated my domain and therefore from many 1 sine has become 1, 1. I have manipulated my codomain and therefore from into it has become onto. And now the situation is very much favorable to me. Sine function from original domain to original codomain was neither 1, 1 nor onto. Then I treated the codomain and restricted it to the range, it became onto. Then I treated the domain in such a manner that it not just becomes 1, 1, but it does not fail to be now onto because I have already treated my function to be onto. So it should not happen that okay, 1, 1ness is established but ontoness is vanished. So ontoness was first established. And keeping that in mind that ontoness should not be disturbed, I have incorporated 1, 1ness also. Fine. So here we can see that if I restrict my domain to minus pi by 2 closed interval, restrict my codomain to minus 1, 1 closed interval, which is the range, the graph which follows is the graph of the sine function, which is both 1, 1 and onto. And therefore now I can talk about the existence of inverse of the sine function. So the heading says inverse trigonometric function. That means inverse function of the trigonometric functions. But it does not tell us that originally when you defined and understood the sine, cosine and all functions, they were not 1, 1 and onto. So over those domains and codomains, I cannot talk about their inverses existence. I will have to treat the domain, treat the codomain, restrict them, make it small, make it very tiny so that my 1, 1ness and ontoness is established. So because sine function from this manipulated domain to manipulated codomain is 1, 1 and onto, therefore there exists sine inverse x from, if it is 1, 1 and onto means this is the range of f, range of the sine function, this is the domain of the sine function. If it is onto means codomain is equal to the range. So this is the range. Sine inverse exists from the range of sine to the domain of sine such that when sine inverse is going to accept any input from minus 1, 1, it is going to send it to that x which is the unique preimage of y under sine. Remember, f inverse y is x if and only if x is the unique preimage of y under f. So sine inverse y is x if and only if x is the unique preimage of y under sine. That means sine of x is y. And this is true for every x belonging in where sine can only act upon. Here, these members, I am only and only talking about sine acting upon those members over the section which belong in the section over which the sine is 1, 1. So x belongs to minus pi by 2 and y belongs to minus 1, 1 closed interval. So for every x coming from minus pi by 2 and y coming from minus 1, 1, this is the setup now. We have established the existence of sine inverse function. Is it understood? So sine function from here to here is 1 and 1 and on to, that means it is bijective, that means it is invertible, and its inverse is existing from here like this. Moreover, two very important properties that we had studied about a function and its inverse was regarding their composition, which is going to be established with sine and sine inverse as well. We know that sine x o sine inverse x, or rather than that, you know how to interpret f o f inverse of x, right? F o f inverse of x is interpreted as f of f inverse of x, right? So similarly, sine of sine inverse x, sine of sine inverse of x, sine of sine inverse x, what will that become? I am talking about f o f inverse. This is equal to identity function on the range of f, which is minus 1, 1. This map applied to x. Sine o sine inverse is identity function on the codomain of the sine function, which is minus 1, 1 closed interval. Identity map when applied to any x coming from minus 1, 1 closed interval is going to give you x only. And similarly, when I talk about sine inverse of sine x, when I talk about sine inverse of sine x, what is this? See, like this also you can understand. Sine inverse is going to act upon only members coming from minus 1, 1 closed interval. This is the domain for sine inverse. Sine inverse can only act upon those x which are coming from minus 1, 1 closed interval. So this x has to come from minus 1, 1 closed interval so that sine inverse can act upon it. Once sine inverse has acted upon it, this member sine inverse of x is going to be pushed inside minus pi by 2 closed interval. Now this was coming from minus 1, 1 closed interval, this complete is coming from minus pi by 2 closed interval, and sine has domain as minus pi by 2 closed interval, so sine can successfully act upon sine inverse x. Similarly, this makes sense when, if I am talking about sine inverse and sine, that means I am only talking about that part of the domain of sine from which, that part of the domain of sine corresponding to which my sine is becoming 1, 1. So here x is coming from minus pi by 2 closed interval, then sine of x is going to go inside minus 1, 1 closed interval, and that is the domain for sine inverse. So sine inverse will then be able to act upon it. So here this will be coming from, or this will be equal to, we know by property, identity function on the domain of sine, which is minus pi by 2 closed interval. This applied to x, and this is again x for all x coming from minus pi by 2 closed interval. Is it understood? These are the features which will be exercised by sine and its inverse function. Now, when we have deduced about the existence of sine inverse, let us graphically try to understand what are the features which it possesses, how does it look like, and how does it actually correspond to being the inverse of sine. So, now we are not interested in this graph of sine function. No, we are not interested. We are interested in that graph of sine function which is corresponding to give me the existence of sine inverse. So, sine x, I am only interested in drawing sine x from minus pi by 2 closed interval to minus 1, 1, because only from here to here it is bijective. When you do that, what do you get? Just draw it from minus pi by 2 closed interval. It would just be drawn in this manner. That's it. I'm just drawing that section of the sines graph. This is minus pi by 2. This is pi by 2. Corresponding to pi by 2, it attained the value 1. Corresponding to minus pi by 2, it attained the value minus 1. This is 0. This is the graph of sine function from minus pi by 2 closed interval to minus 1 closed interval. And this is a 1 1 on 2 graph. Right? You can see it's 1 1. You draw any horizontal line across the graph, it will be intersecting the graph at exactly one point. And if I talk about any element coming from minus 1 1 closed interval, it has a unique pre-image in minus pi by 2 closed interval. Right? You pick up any member, you pick up this member, it has this as its pre-image. You pick up this member from minus 1 1 closed interval, it has this unique pre-image. You pick up this member from minus 1 1 closed interval, it has this as its unique pre-image. Right? So this is definitely 1 1 and on 2. Now, I am interested in the graph of sine inverse. Now what happens is, now I am going to teach you a drill. Something that is going to always help you in your entire life to draw a graph of the inverse function from the given function's graph. If you are given the graph of f, how to get the graph of f inverse? I am wanting the graph of sine inverse x, which I know is from minus 1 1 closed interval to minus pi by 2 pi by 2. How to get its graph? The domain will be minus 1 1 closed interval and the codomain will be minus pi by 2 to pi by 2. How to get the graph? Come back to the graph of the function. Draw the line y equals x. This is the line y equals x. We have learnt this graph, right? Y equals x. What you do is you let this line act as mirror for you. You let this line act as mirror for you. What did I say? Let this line act as mirror for you. And you take the mirror image of this graph corresponding to this mirror, which is this line. When you take the mirror image, what you get is, this comes as the mirror image, the dotted part of the graph. I am just taking the mirror image of the drawn graph of sine function. This comes as the mirror image corresponding to the mirror, which is the line y equals x. Just draw this dotted line here and you have your graph of sine. That is it. This is the graph of sine inverse. What is the domain of sine inverse? It is minus 1, 1 and this is minus pi by 2, pi by 2. This is the graph of sine inverse function. And that is how you obtain from the graph of sine the graph of sine inverse. Is it clear? Now that we are through with this, let me talk about a certain specific approaches related to sine and sine inverse. See, if I again draw the graph of sine over its original domain and codomain, let me just tell you about certain observations. See, how did we obtain sine inverse? By restricting our codomain to the range and restricting our domain to such a section corresponding to which there was no turn in the graph and the ontoness was not disturbed. This was the criteria. Now, let me go back to the graph of sine from collection of all reals to collection of all reals. If I draw the graph once again of the sine function, how was it? It was just like this. It went on oscillating and that's it. Right. So here you know this was 1, maximum height was 1, minimum was minus 1, this is 0, this is pi by 2, this is pi, this is 3 pi by 2, this is 2 pi, this is 5 pi by 2, this is 3 pi. So on here as well, this is minus pi by 2, this is minus pi, this is minus 3 pi by 2, this is minus 2 pi and so on. See, one thing you understand, what we have done, I'm going to write that, and what we could have done, what are many more options there with us that we are going to understand now. We understood that from minus pi by 2 to minus 1, 1, sine function was bijective. Clear? If I restrict it from minus pi by 2 comma pi by 2, I see that the graph is not having any turns and ontoness is not being disturbed because all the values from minus 1, 1, 1 are being covered. If you, instead of restricting the real line to minus pi by 2 closed interval, would have restricted the real line to pi by 2 to 3 pi by 2 closed interval, this closed interval if you would have restricted to, again the graph that would have come would have not had any turns. And it would again be covering all the values from 1 to minus 1 or minus 1 to 1, and therefore again 1, 1ness and ontoness would have established. So I can say that from pi by 2 to 3 pi by 2, from here to this interval, again sine function is 1, 1 and onto, right? Sine function is both 1, 1 and onto. From here to here as well as here to here. Or what we could have done, minus 3 pi by 2 minus pi by 2. If this would have been my restricted domain, the graph which would have followed would have been like this. And you can again see that it does not have any turns and it is covering all the values in this range of minus 1, 1. So from minus 3 pi by 2 to minus pi by 2, from this interval to minus 1, 1, again sine is 1, 1 and onto, right? And this would have been just proceeding. If I would have taken it from 3 pi by 2 to 5 pi by 2, again I would have got this graph which is not having any turns and covering all the values from minus 1, 1. Or if I would have restricted from minus 5 pi by 2 to minus 3 pi by 2, I would have got this graph, this part of the graph which is again having no turns and is covering all the values from minus 1, 1. So again from 3 pi by 2, 5 pi by 2 to minus 1, 1, or from minus 5 pi by 2 minus 3 pi by 2 to minus 1, 1, again sine is 1, 1 and onto. And that is going to happen. So many sections can be there. If I keep on increasing the oscillation, so many sections are going to come up here, so many sections are going to come up here, to which if I restrict my domain, letting my range to be the same, obviously sine function is 1, 1 and onto. So let me write it like this, that sine x from here to here or here to here or here to here or here to here or here to here is bijective. If sine function is bijective from here to here or here to here or here to here, there are so many ways in which it is bijective. That means what? What does it mean? This means there exists sine inverse x not just from minus 1, 1 to minus pi by 2, but sine inverse x can also be existing from minus 1, 1 to minus 3 pi by 2 minus pi by 2, minus 1, 1 to pi by 2 to 3 pi by 2, minus 5 pi by 2 minus 3 pi by 2, 3 pi by 2, 5 pi by 2, and so on, right? I can talk about sine inverse existence not just from minus 1, 1 to minus pi by 2, but from minus 1, 1 to so many subintervals. What happens is each one of them is called a branch of sine inverse x. What I have drawn corresponding to this part of sine function, the sine inverse graph that I had drawn, was a branch of sine inverse. It was a branch of sine inverse. Each each of these sine inverse x's that you can see from here to here, 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 all these are called branches of sine inverse x. Each of these is called a branch of sine inverse x. Okay? This is one branch of sine inverse x, this is other branch, this is other branch, other branch, other branch. Branch by branch, I mean, see what is going to happen is, right now what you did, you restricted the graph of sine function to this subinterval, and then you applied your approach of taking the reflection across the line y equals x to get the graph of sine inverse from -1 closed interval to minus pi by 2 pi by 2. So corresponding to this section, you obtained a branch of sine inverse. When you are going to restrict your sine function to say pi by 2 to 3 pi by 2, corresponding to that, some other part of sine function's graph is going to come. Then again you are going to take its reflection along the line y equals x to get the graph of sine inverse, which is going to be from -1 closed interval to pi by 2 3 pi by 2 closed interval, and that is going to be another branch of sine inverse, right? That is why each of these is called a branch of sine inverse function, but the branch which we considered, which was from -1 closed interval to minus pi by 2 pi by 2, it is called the principal value branch of sine inverse x. Sine inverse x from -1 closed interval to minus pi by 2 closed interval is called principal value branch of sine inverse x. Why principal value branch? This is one branch of sine inverse x. For sure, this is one branch of sine inverse x. Sine inverse x from -1 closed interval to minus pi by 2 is one branch, but this is called the principal value branch. Why? I'll tell you. See, sine inverse x is a function from -1 closed interval to each of these, and it is 1 on 2. Sine is 1 on 2 from here to here, sine inverse is 1 on 2 from here to here. Sine is 1 on 2 from here to here, sine inverse is 1 on 2 from here to here. 1 on 2 means what? Each element from -1 closed interval is going to have a unique image in this interval. Each element from -1 closed interval is going to have a unique image in this interval, unique here, unique here, unique here. So every element in -1 closed interval is going to have one exact image here, one here, one here, one here, one here. Whatever image it has in here, that is called the principal value of that element. Are you understanding? Whatever answers or images each element from -1 closed interval has in this interval, they are called the principal values. Okay? It is having image here also, here also, here also, here also. But whatever images are here, they are called principal values, and therefore this branch which is giving the principal values corresponding to each element of -1 closed interval is called the principal value branch. So if somebody asks you to give the principal value of sine inverse 1, you have to search the answer in this interval, not anywhere else. You have to consider the principal value branch and find out the answer of sine inverse 1, which is going to be lying in minus pi by 2 closed interval. Is it understood? Revise everything very nicely. We are going to talk about some more features, applications of all of this, and we are going to move ahead with understanding how to get cosine inverse, tan inverse, and so on. So I'll see you in the next lecture. Thank you.